Okay, so in this section, what we're going to do is we're going to look at our trig functions with respect to right triangles. And recall that in our coordinate system, we formed right triangles by looking at some ray, where we would form an angle by having an initial side, a terminal side, and in this case, I have a point xy at B. If I draw a vertical line down from B to the x-axis, I've formed my right triangle. We had done this prior with a unit circle where the r value was 1, but now we're just going to look at any r value. And prior with the unit circle, for example, our sine with the unit circle, and I'll use a different angle, I'll call it theta. That was equal to y. So sine was y, cosine was x, and so on. But we can write this as y over 1, where that denominator 1 was the radius of our unit circle. Now that we're working with any radius, our sine value, and here with respect to this angle A, is now the y value over just any r value. So again, we're going from the unit circle to any radius r with respect to an angle theta. And then we're going to take these triangles and we're going to move them away from the coordinate system. So let's first look at a generic triangle, and this is going to be true for all triangles, not just right triangles. So it's something to keep in mind as we go through the rest of this course, is that with any triangle, doesn't have to be a right triangle, the sum of the angles is 180 degrees. And they also have this really nice property where corresponding angles and sides will have similar size, and I'll tell you what I mean in just a second. So let's look at B. If I look at angle B, when I say corresponding side, corresponding is the side opposite. So the side that corresponds to angle B is side B. And if angle B just happened to be the smallest angle of the three, then side B would have to be the smallest side of all three sides. If I look at angle A, it corresponds to the opposite side, which I'm going to call A. And let's say that A is the largest angle. Then that would mean side A would also have to be the largest side. And then if we look at angle C, the side opposite of the angle is the corresponding side, so I'm going to name it C as well. So uppercase C for the angle, lowercase c for the side. Again, don't have to use these letters, they just make sense. And that's the important thing about our triangles. Largest angle goes with largest side, smallest angle, smallest side, medium angle goes with medium side. When you're solving problems, that's a really quick check, is to just look at the triangle and say, okay, do my answers make sense? So that will come up quite a bit. But now what we want to do is we want to review that idea of SOHCAHTOA. So SOHCAHTOA is just a way to remember sine, cosine, and tangent values given any right triangle. So when we're looking at a right triangle, and something to remember is that our Pythagorean theorem, a squared plus b squared equal to c squared, that's still true, but in this case, a is x squared, b is y squared, and c squared, which is usually the hypotenuse, would be the r squared here. That's going to come up as well. Now when we talk about the sine of this angle A, sine is going to be the side opposite, which is that y value, over the hypotenuse, which is r. And that's where our SO comes from. S for sine, O for opposite, H for hypotenuse. And then we look at CA, that's cosine adjacent, which is our x, hypotenuse is r. So cosine, adjacent, hypotenuse, and adjacent just means the side next to the angle. So in this diagram, X is the side next to angle A. And our last is our TOA for tangent, which is opposite over adjacent. So that's where the SOHCAHTOA comes from. And it's just an easy way to remember the relationship between angles and sides when we're looking at sine, cosine, and tangent. Now, I don't know of any mnemonic device for cosecant, secant, and cotangent, but basically they're just reciprocals of sine, cosine, and tangent. So if you have sine, cosine, tangent, flip them, you get cosecant, secant, and cotangent. In example 1, we're going to find the values of all 6 trig functions for both angles A and C. So if I look at angle A, and I'll start with sine of A, that would be the opposite side to A, which is the 24, over the hypotenuse, which is 30. And then if I reduce by 6, I get 4/5. So if you wanted to relabel this to remind yourself, A, B here is the hypotenuse, or the 90-degree angle, so 30 would be the hypotenuse. And then C goes with side 18, so that would be the side opposite. But we're looking at angle A. So with respect to angle A, the side opposite is 24, the hypotenuse, which is always the longest side, is going to be 30. Cosine is going to be the side adjacent, which is 18, over the hypotenuse, which is 30. And that reduces to 3/5. If I look at tangent, with respect to angle A, it's going to be opposite over adjacent, which would be 24 over 18, reduces to 4/3. And I'll go to cotangent because it's just flipping tangent. So it should be 3/4. Or you could use that if tangent is opposite over adjacent, cotangent is adjacent over opposite. That would be 18 over 24, and then you would have to reduce. Why don't we go to cosecant of A? Well, that's just a reciprocal of sine, so that would be 5/4. Or if sine is opposite over hypotenuse, cosecant is hypotenuse over opposite. And then last would be our secant. I'm just going to flip cosine to get 5/3. Now let's look at angle C. It helps to be able to look at all the different angles and find the values, because these triangles don't necessarily have to be sitting in the usual spot, and I'll draw what I mean here. So typically when you see a right triangle, it sits kind of like that with the right angle at the bottom. But we can rotate these all over the place. So I just want to make sure that you can find, with respect to any angle, side opposite, side adjacent, hypotenuse, and so on. So sine of C would be opposite, which is 18, over hypotenuse, which is 30. So with respect to a change in angle, we have a change of side opposite, side adjacent. Hypotenuse doesn't change. So cosine of C is going to be adjacent, which is 24, over hypotenuse is 30. And that reduces, oops, I forgot to reduce the first one to 3/5. And then cosine would be 4/5. We'll look at tangent of C. Tangent of C is going to be, with respect to C, it's going to be opposite, which is 18, over adjacent, which is 24. And then that will reduce to 3/4. Cotangent of C is going to be, I'm just going to flip tangent to get 4/3. Cosecant of C, I'm going to flip sine to get 5/3. And secant of C, I'm going to flip cosine to get 5/4. So not only what did I want everyone to get practice of looking at the different angles and getting comfortable with identifying the opposite side, the adjacent side to the respective angle in the hypotenuse, but I also wanted to point something out. Notice that if I look at sine and cosine with angle A and then look at angle C, they're switched. Sine of A is equal to cosine of C. Cosine of A is equal to sine of C. Look at tangent, cotangent. Also, think about the graph of sine and cosine. They're similar, right? They're shifts of each other. So this makes sense. Same thing happens with tangent and cotangent. Their graphs are very similar. They're not quite shifts of each other, but they go through the same values, but just for different angle measures. So they're flips as well. Tangent A is equal to cotangent C. Cotangent of A is equal to tangent of C. And the same thing with cosecant and secant. Their graphs are similar. They're just shifts of each other. So these values will be similar or will be equal as well. So cosecant of A is equal to secant of C. Secant of A is cosecant of C. So these are called cofunctions. So sine and cosine are cofunctions. Tangent, cotangent are cofunctions. Cosecant and secant are cofunctions because they go through all the same values, but just for different angles. And something to notice with a right triangle is B in this case is 90 degrees. So that must mean that A and C will add up to 90 degrees. They complement each other. So their cofunctions will complement each other as well. We'll go into more of that later on. But let's look at some special triangles that come up once in a while. And that would be a 30-60 and then a 45-degree triangle. So we're going to create the 30-60 triangle. And when we say 30-60 is because this is going to correspond to 30 degrees, 60 degrees. So some common values that we have on our unit circle like pi/6, pi/3. We'll look at an equilateral triangle. Equilateral meaning all sides are equal. And necessarily if all sides are equal, all angles are equal. In this first example, I have an equilateral triangle with sides of length 2. Now, if I were to draw a vertical line cutting this triangle in half, what I've done is I've formed two right triangles. Since I cut the top angle in half, the 60 goes to 30 and 30. And since I've cut the base in half, the length of each side is of these two triangles are 1 and 1 since the total length was 2. And that brings me to my next diagram here. With that triangle, I've formed two right triangles. And I know that one side is a length 1 at the bottom here. And I know that the hypotenuse is 2. So let's go ahead and figure out what our x value is. And here we're just going to use our Pythagorean theorem. So remember that if you take the smaller sides, so this would be x squared plus 1 squared, and square them, it's going to be equal to the square of the hypotenuse. And here the hypotenuse is 2. That's our longest side. Solving for the x squared, I'll get 4 minus 1, which would be 3. So x is going to be plus or minus the square root of 3, but we just use the positive because we're talking about the length of a side. It's impossible for it to be negative. So that gives me that x is equal to the square root of 3. Which brings us here to our 30-60 triangle. It's a very special triangle. It has sides of 1 and square root of 3 and hypotenuse of 2. From that, remember 30 degrees corresponds with pi/6, 60 degrees corresponds with pi/3. If you look at the values of the unit circle and you think of the values of sine and cosine and so on, let's just look at that 30 degrees. Okay, so again, 30 degrees is pi/6. think about sine of 30 degrees, or pi over 6. In the first quadrant, that's 1/2. And that's because it's the opposite side with respect to the angle 30 degrees, which is 1, over the hypotenuse, which is 2. Cosine of 30 degrees, or pi over 6, would be adjacent, square root of 3 over hypotenuse, which is 2. Now that's where those pi over 6, pi over 3, where those values come from on our unit circle. And then we have another special triangle, which is our 45-degree triangle. And this is an isosceles triangle, isosceles meaning that two of the legs are the same length. Here, both of the legs or sides, both of the sides are 1, and the angles are 45. So in this particular case, if you have a side of 1 and another side of 1, then you would have 1 squared plus 1 squared is 2. Our hypotenuse would be the square root of 2. And then if we look at sine, we'll go to, and it doesn't matter because they're both the same, right? They're both 45 degrees. If we look at sine of 45 degrees, which is our pi over 4, I'll leave it as degrees. Sine that's going to be opposite over hypotenuse. So 1 over the square root of 2, but remember we rationalize. So that gives us our square root of 2 over 2. So sine of 45 degrees is square root of 2 over 2. And since this triangle has the same angles, 45, 45, remember when we looked at, if I called this A and the bottom one B. So remember we looked at sine of A is going to be cosine of B, cosine of A is sine of B in our prior example. Now you can see why sine and cosine both have the same value of square root 2 over 2 is because the angles are the same. So with respect to angle A, if I was looking at angle A, I would have adjacent, which is 1 over the square root of 2. Rationalizing, I get square root 2 over 2. So those are our special triangles that give us those points, those nice points along our unit circle. In example 2, we want to find the value of all 6 trigonometric functions for 30 degrees and 60-degree angles. So let's start with sine of 30 degrees. So sine of 30 degrees, if we look at the triangle, it's going to be 1/2, and we already looked at that earlier. Cosine of 30 degrees, if we looked at our 30-60 triangle, is going to be square root 3 over 2, because it's going to be the side adjacent over the hypotenuse. Again, we looked at that earlier. So again, I'm looking at the triangle right above, right? The 30-60, and then we have our 90 degree, where x is square root of 3. So if we're looking at tangent with respect to the 30 degrees, tangent would be opposite over adjacent, so it's 1 over the square root of 3. And then we rationalize. I'm just going to write square root of 3 over 3. I rationalize in my head, I multiply top and bottom by square root of 3. And then cotangent of 30 degrees is going to be adjacent, which with respect to the 30 degrees, adjacent is going to be the square root of 3 over opposite is 1. I'm not going to write the over 1. Cosecant of 30, I would just flip sine to get 2. And then secant of 30, that would be flipping cosine, I would have the square, or 2 over the square root of 3. Or you could look at it as hypotenuse over adjacent. And then rationalizing by multiplying top and bottom by the square root of 3 gives me 2. square root of 3 over 3. So those are all the values that we expect when we're thinking about 30 degrees or pi over 6. Going to the unit circle, those are all the values we have. And then if I was going to look at the 60 degrees, and I'm just going to do a few of these. Again, going back to the triangle, this time we're looking at the 60 degrees. So the side opposite is going to be the square root of 3 over the hypotenuse, which is 2. But then notice that that's our cosine value. So again, these complementary angles, sine cosine, are going to be the same, which tells me that cosine of 60 degrees should be equal to 1/2. And I know these values are true. We've looked at them with the unit circle. We've looked at them a lot. But now we're looking at them with respect to this special triangle. And I can see that sine cosine, sine of 30, cosine 60, they're the same. If we look at tangent with respect to 60, it's going to be opposite, which is square root of 3 over adjacent, which is 1, and that's cotangent. So I want blue. Tangent of 60 degrees is going to be square root of 3. And then when we look at cotangent of 60 degrees, it's going to be 1 over square root of 3. Rationalizing gives me square root of 3 over 3. Exactly what I expect because these guys are cofunctions. Cosecant of 60 degrees, we would be flipping sine of 60 and rationalizing. And it's the same as secant. Secant of 60, we would be flipping cosine. So 1/2 goes to 2. And it's the same. So again, as I mentioned before, sine cosine, tangent cotangent, cosecant secant, these are what we call cofunctions. And that would be this box down here. These are our cofunction identities written in both degrees and in radians. Oh, it looks like the PDF did not print well. So I'm just going to have to rewrite over this. So sine of A is cosine of, this should be a 90 degrees, minus A. So these little weird symbols, these are degree symbols. When I converted my document, I think it converted those symbols. So if you have sine of some angle A, it's going to be equal to cosine of 90 degrees minus A, because remember those two angles add up to 90 degrees. And same with cosine. If you have cosine of A, it's going to be equal to sine of 90 degrees minus the angle A. But we could also be working in radians. So this weird P, again, the typesetting changed when I saved it to a PDF and I forgot to check. That P is for pi. So all of these P's are pi. So 90 degrees is pi over 2. So if we're looking at our cofunctions in terms of radians, it would be pi over 2 minus the angle. We'll use those in example 3. If I were to write the expression in terms of its cofunction, well, I'm given sine. So that just means I have to write sine equal to, its cofunction is cosine of 90 degrees minus the angle. In this case, A is 54 degrees, minus 54 degrees. That means that cosine, it's going to be 90 minus 54 is 36. And now it's okay to keep the parentheses around, but if you want to drop them, you can drop them as well. Let's try another one. We have cotangent. Cotangent, its cofunction is tangent. So I know this is equal to tangent of, and here I'm in radians, it's going to be pi over 2 minus my angle, which is pi over 5. So this is going to be tangent of 5 pi over, wait, 10, right? 5/10, I can't add. 5 pi over 10, 2 pi over 10, I believe. Simple math escapes me. So this will end up being tangent of 3 pi over 10. So once you have one function, you can always get the cofunction by subtracting from either the 90 degrees or from the pi over 2. Again, I can leave the parentheses on or drop them. Something I wanted to point out is, remember with radians, you don't have to write the units, but with degrees you do. So the next thing we're going to talk about is this idea of a reference angle. So a reference angle, and we're going to be using this weird asterisk, not asterisk, accent mark, sorry. And this accent mark, in math, it's prime. Accent mark, hash mark, what other things do we use for it? Regardless, that stands for prime, and if our angle is the Greek symbol theta, then this is pronounced theta prime. So that's not just a smudge of ink, that's actually how we write the reference angle. So for any angle, if you put that little prime on it, it's reference angle. So the reference angle is going to be the smallest angle from the terminal side of theta to the x-axis. Okay, so it's the smallest angle that can be formed from that ray, terminal side ray, to the x-axis. So let's just say that we're looking at this angle theta, and theta happens to be in quadrant 1. Well, I have a choice. When I'm looking at the distance from this terminal side to the x-axis, I can look at this distance in quadrant 1, or imagine that if I kept going around, I can also get to the x-axis. So it's not the positive x-axis, which is usually what we talk about, it's the whole x-axis. What we're doing is we're taking that terminal side, that ray, and we're forming two angles. One will go right, the other left, and whichever one is smallest will be the reference angle. So if your angle, theta, falls in quadrant 1, then the smallest distance will be theta. So our reference angle is equal to the angle, because the shortest distance from the terminal side to the x-axis is that angle theta. But if you're in quadrant 2, here we have our angle theta landing in quadrant 2, and you think about that terminal side. Well, to get to the x-axis, I can keep continuing on, or I could go back where I started from. I have these two angle measurements to choose from. I always choose the smallest, which means my reference angle is going to be that smallest distance to the x-axis. In this case, it's going to land on the negative side of the x-axis. So if you wanted to compute what that reference angle is, if you look above, there's a little formula. So in quadrant 2, your reference angle theta is going to be, the total distance is 180 degrees, and if you just subtract theta, what's left over will be your reference angle. And now in quadrant 3, if I look at my angle theta, and I look at that terminal side, I need to get back to the x-axis. I can either come back the way I came or keep going. Those are the two angles to choose from. The smallest angle would be this reference angle theta, going to the x-axis on the negative side of the x-axis. So if you think about this, If you took away 180 degrees from theta, what's left over would be the reference angle. And that's why our reference angle is going to be our angle theta minus 180 degrees. So trigonometry is geometry. It's very visual. You can always draw pictures to represent everything if you forget. So you don't have to memorize these formulas. You could just draw an angle and go, oh, okay, this would be the closest one. What makes sense? How can I get that angle? In quadrant 4, our theta is going all the way around, landing in quadrant 4. So when I look on that terminal side, I can keep going, or I can go back the way I came, choosing between those two angles. Our reference angle would be if we just kept going to the positive x-axis. So if you look at the whole 360 degrees and you just take away theta, what's left over would be your theta prime, your reference angle. And that gives us our formula. The reference angle is 360 degrees minus theta. So oftentimes it's easier for us to work with reference angles because they're acute angles. They're between 0 and 90 degrees. So they're actually, if you were just looking at the first quadrant, those are all our 0 to 90 degree angles, which is our reference angles, are all between 0 and 90 degrees. So basically, if you're trying to figure out a trig function, a value of a trig function, you know what quadrant they're in. All you have to do is figure out their reference angle value and then just make it negative or positive depending on what quadrant we're in. Something to remember when you're finding reference angles is you have to make sure that the angle theta is on one rotation of the circle. So if you're working in degrees, the angle theta that you're given has to be between 0 and 360 degrees in order for you to find the reference angle. If you're given the angle in radians, it has to be something from 0 to 2 pi to be able to find the reference angle. In example 4a, we're given degree 222 degrees. So that is something between 0 and 360. What I notice is that 220 degrees, that should be in quadrant 3, because quadrant 1 is 0 to 90, quadrant 2 is 90 to 180, quadrant 3 is 180 to 270. So I know I'm in quadrant 3. And that means my reference angle is going to be equal to theta, which is the 222, minus 180. And that means my reference angle is 42 degrees. In part B, I have 11 pi over 6. 11 pi over 6, that would be in quadrant 4. In quadrant 4, to figure out my reference angle, I would have to take the total distance, and I'm in radians now, which is 2 pi, and I would subtract the theta, which is 11 pi over 6. So 2 pi just turns into 12 pi over 6 minus 11 pi over 6. And I get pi over 6. So that's just a check. If you're trying to find the reference angle and you get something that is negative or something that is larger than 90 degrees or larger than pi over 2, then you did some math wrong. Yeah, so just double check and make sure the angle that you're using is within one rotation of the circle. So if we look at C, C is 1,000 degrees. Well, the circle only goes up to 360 degrees. I'm going to have to first keep subtracting 360 till I get to something between 0 and 360. So if I minus 360 degrees, I get 640 degrees, still too big. Subtract 360 again, I get 280 degrees. Okay, so that is something between 0 and 360, and that's also in quadrant 4. Quadrant 3 is 180 to 270, 270 to 360 is quadrant 4. So in quadrant 4, to find your reference angle, you would take the total 360, because I'm in degrees, minus the 280, which means my reference angle is going to be 80 degrees. If you prefer, you can draw pictures of these angles similar to the 4 boxes we have above to get an idea of how you would find the reference angle, but it's not necessary. You could just use those formulas. So now we're going to use a reference angle to find the exact value of sine of 330, cosine of 225, and sine of 5 pi over 6. Again, we could just look at that whole unit circle and figure out what it is, but this is how you would use the reference angle. In part A, sine of 330 degrees, well, 330, that would be in quadrant 4. So I know that whatever this is, it's going to be negative because sine is negative in quadrant 4. So if I were to use a reference angle, it would be in quadrant 4, it's going to be 360 minus 330. So that's going to be negative sine of 30 degrees, because that's our reference angle. And that's going to be 1/2, but it's a negative. So it's negative half. Cosine of 225. When I look at 225, that should be in quadrant 3 because that's between 180 and 270. In quadrant 3, cosine is negative. So this is going to be negative cosine of my reference angle. In quadrant 3, it would be 225 minus 180. And that should give me 45 degrees. So cosine of 45 degrees is square root 2 over 2, but this is going to be a negative square root 2 over 2. So again, just another way that you can compute trig functions. I don't know if you've noticed, but you have a lot of choices when we deal with trigonometry. Again, that's going back way back in the beginning when we looked at the unit circle and we looked at all its symmetry and all the patterns that come from the unit circle. All that symmetry, all those patterns, what that gives us is a lot of different ways to figure things out. Let's see, sine of 5 pi over 6. So 5 pi over 6 is in quadrant 2. Sine is positive in quadrant 2. So this would be equal to a positive sine of 5 pi. Oops, I'm in quadrant 2. Oops. Sine of pi minus 5 pi over 6. I was doing this backwards. It's going to be sine of, so this would be 6 pi over 6. Sine of pi over 6. And sine of pi over 6 is a positive 1/2. Still positive in quadrant 2. Okay, so now what we're going to do is we're actually going to solve for the angle. In all of our examples, we were given angles and then we were trying to find the trig values with respect to that angle. But what if you had the value, you had to go back and figure out what angle corresponds to that value. In example 6, it says find the acute angle in radians. So just make sure that you're working in radians here. That satisfies the equation, give the exact value, and then approximate using a calculator. So it's specifically telling us to find an acute angle. So remember that an acute angle that is in radians. That will be an angle from 0 to pi over 2 radians. Example A, we have sine of theta is equal to 1/2. So I have to figure out what angle theta will give me a sine value of 1/2. And if we just do a quick sketch, positive value, sine is positive in quadrants 1 and 2. So at least I know my theta has to be in quadrant 1 or in quadrant 2, because that's where sine is positive. And if I look in quadrant 1, that would be at pi over 6. So sine of pi over 6 is a positive 1/2. But it's also true that 5 pi over 6, sine of 5 pi over 6 is a positive 1/2. And now these are not my only two answers. Remember, we can go around infinitely many times. So if I add 2 pi to pi over 6, I have another angle where sine is going to be equal to a positive 1/2. If I add 2 pi to 5 pi over 6, if I keep adding 2 pi to these values, or even subtracting 2 pi, going in the other direction, I'm going to get infinitely many angles that give me a sine value of 1/2. And you can see that by remembering the graph of sine, how it goes on infinitely in the x and y plane. It goes on infinitely in both directions. And that's why in the directions it says specifically to find the acute angle. And that's just telling you, okay, you don't have to list infinitely many solutions. Just give me the angle that's between 0 and pi over 2. And that would be pi over 6. So this would be the theta value that they're looking for. Whenever we're actually solving an equation for the angle, and we'll go over this idea of inverse trig functions in a later sections, but that's actually what we're using. So if we were going to use a calculator to approximate the value of sine of theta equal to 1/2, it depends on what calculator you're using. Sometimes calculators will have this symbol. That means it's the inverse function, and that's what you would use. If you don't see that symbol in your calculator, you will probably have to do second sine. And what that does is it allows you to, for example, if you did have second sine, and it depends on your calculator. In my calculator, if I did second sine, I would then do the 1/2 and equal. But in other calculators, it is the other way around. You would put the value 1/2 in first and then do second sine. But regardless of what calculator you have, this second sine key, this means sine inverse. And then in our case, we're putting in 1/2. So you're either going to do 1/2 second sine or second sine 1/2. And what you'll get is you'll get theta is approximately equal to, again, make sure you're in radians. In my calculator, I get 0.5235987. You might have a different length on your decimal. It just depends on what calculator you're using. When you use your calculator to figure out what an angle is, it will always give you a value that's only one value. So in this case, it only gave me this 0.5. So in radians, think about the unit circle. Quadrant 1 goes from 0 to pi over 2. Pi over 2 is approximately 1.6. So 0.5 is in quadrant 1, so that gave me the pi over 6. I could double check this. I can double check this by just putting pi divided by 6 in my calculator and seeing if it is 0.523598878, and it is. Okay, so pi over 6 is the exact theta value that gives you the acute angle where sine is positive 1/2, but theta is approximately equal to 0.523598878, and we're not rounding that. That'll be typical of many trig problems. You're not going to round them because once you start rounding these theta values too much, it really throws off your answer. Let's try this again with tangent of theta equal to 1. Well, if I did look at a graph, tangent of theta is equal to positive 1 in 2 quadrants. Tangent is positive in quadrant 1 and in quadrant 3. So in quadrant 1, that would be at pi over 4. In quadrant 3, that's 5 pi over 4. So again, I'm choosing the acute angle, and that would be positive pi over 4. So the theta that I'm looking for is pi over 4. In my calculator, if I were to put in that second sine or sine inverse key, and I put in 1, and here you're using second tangent or tangent inverse, depending on the calculator you're using, and you're putting in 1, you should get theta is, oops, approximately equal to 0.785398163. So that's what shows up on my calculator. Again, yours may go out longer or be a little bit shorter. So just write down whatever you have on your calculator. And that would be the approximation. So my second tangent 1 is going to be equal to that. Now I could double check this by just putting pi over 4 into my calculator, and I should get the same decimal approximation. And this answer does make sense because if the answer is pi over 4, that would be an angle in quadrant 1. 0.78 is in quadrant 1. In that example, we actually had exact values that we knew from our unit circle. But what if we don't? In example 7, it says find all angles. So we have to be careful about this because it's not just an acute angle, it's all angles. And it's telling us in this interval from 0 to 360 degrees. So one thing you have to make sure of is you have to make sure that your calculator is in degrees. So we want to find all the angles theta that satisfy this given equation that sine of theta is approximately equal to 0.5136299. Okay. So again, sine is positive. I know I'm in quadrant 1 or quadrant 2. And these are just from 0 to 360. So I'm just going around 1. So that tells me I'm going to have 2 angles. I'm going to have something in quadrant 1 and something in quadrant 2. I don't know the exact value because the 0.5136299, I have no idea what that is. All I know is it's positive, so I know what quadrant I'm in. And I should get 2 answers. So one thing I could do is put this in my calculator. Again, make sure that you're in degrees. So in my calculator, if I do the second sine and I put in the 0.5136299, I get a theta value that's approximately equal to, this is degrees now, 30.905919949. Did I get them all? I think so. Degrees, these are degrees. So it's about 31 degrees, and that makes sense because this, the 0.513 blah, 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 is about 1/2. So it should be about 30 degrees. That answer makes sense to me. But that's just one. I know I'm going to have 2 values. So we're going to use a reference angle to find the second one. So we are trying to find the angle in quadrant 2. So I know my reference angle would be the shortest distance from that terminal side to the x-axis, sorry. But look, these distances are the same. Remember, the reference angle is a value between 0 and, we're in degrees here, so 0 to 90 degrees. These are the same. So when you think about that, all I have to do is take this total distance around, which is 180 degrees. And if I take away that first angle that I got, what remains will be the angle that I'm looking for. So we're going to take our other theta value, which would be 180 degrees, the total distance, and we're going to minus our reference angle. So our reference angle is the first angle we got, so 30.9058. I can't read my own writing. 91949. And then when I put that in my calculator, I got 149, and that makes sense. About 150 degrees. Yes, that would be in quadrant 2. 0.090400805. Again, there's so many errors that could happen with your calculator, so you just have to make sure that the answers make sense, right? I know that I'm going to get angles in quadrant 1 and quadrant 2 because sine of theta is positive. So I got these two angles. 31 degrees, that's in quadrant 1, 150, about that would be in quadrant 2, so I'm actually okay. So let's try another one. Let's do example 8. In example 8, it says find all angles. So again, we're looking at all angles, but it's giving us an interval. This time our interval is in radians, so just make sure you switch your calculator to radians. We're going from 0 to 2 pi, so one circle around our normal circle. This is cosine. Cosine is negative 0.925965. So since it's negative, cosine is negative in quadrant 2 and in quadrant 3. So that tells me I'm going to get two angles. One of them will be in quadrant 2. The other will be in quadrant 3. Just do a little sketch here. So negative. And I don't really know where I'm going to sketch the angle, so I'm just going to sketch two random angles. Okay, so I'm going to use my calculator, and this time I'm going to be doing second cosine because it's a cosine function. Depending on your calculator, since this is a negative value, you might have to use that plus minus key. So you might have to put in the 0.9259655 and then do the plus minus key to make it a negative, and then do your second cosine. So in the calculator, when I did this, I got I'm in radians now, right? 2.754380841. Okay, so in radians from, is that in quadrant 2 or 3? Okay, so radians, right? This would be 0, pi over 2 is about 1.6. This is 3.14 because it's pi. So 2.75 whatever. Yeah, that's in quadrant 2. So this gave me my theta value in quadrant 2. So remember, your calculator will always just give you one value. You have to figure out what quadrant you're in to figure out how you would get the second. Okay, so something I notice is that these two, even though my drawing is kind of funky, maybe I can erase that. Okay, I don't know if I made it worse. Is these will be the same. So I have some choices. I know this angle 2.75, blah, 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 blah. So I could take 100 or take the pi, that total distance, which is pi, and if I just knew this angle here, I'll call it a reference angle. If I just knew that angle, then if I take 100 or pi minus that reference angle, that would give me my first angle. So since these values are the same, if I took pi and I added that reference angle, that would give me this second angle here that goes all the way around to quadrant 3. So that's one option. And there will be many ways that you can see these problems. So again, to figure out my reference angle with respect to that first angle theta that I got, I would do pi minus that theta. And then in my calculator, so pi minus 2.75, la, 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 la. Let me see. Okay, so it looks like I got 0.3872118.126. So this angle is that reference angle. So if I just take that angle and I add it to pi, that would give me my angle in quadrant 2. So that's just one way to do that. So let me go ahead and take that angle and add it to pi. Okay, so it's approximately 3.5288.044, and I have 66 in my calculator. Okay, does that make sense? In quadrant 3, we're going from 3.14 to about 4.7. So yes, that would be an angle in quadrant 3, but that's not the only way we could have looked at this diagram. If I go back to this diagram, and let me go ahead and draw another, maybe I should have kept that there and just drawn another one. If I go back to this diagram, so remember we had angle, angle. If we look at our first angle theta, notice that that's going to be the same distance if I went in the other direction. So once I found this first angle theta, if I took theta away from 360, if I just subtract it from 360, I would be taking this distance away. And what would be left over is the angle that I wanted. So another way we could have figured out our second angle was taking 2 pi and just subtracting that initial theta, which would give us our second angle. So again, more than one way to look at it. But again, once you get your answer, make sure it makes sense. For one, if this was 27 instead of 2.7, I could have had a calculator error, or maybe I was in degrees and not radians. So just make sure that the theta answers that you get make sense with what you're asked to find. So that's it for this section. We're going to go back again to this idea of inverse functions and solving for an angle in a later section. So this is just a short introduction to that.